Welcome to the third series of lectures on Math 232, Real Analysis. So in this lecture, we will discuss properties of contents and premeasures. So to start, we consider the following theorem. So here we have a ring R on a set X and a content mu defined on the ring on X. So by a content, recall that here the content of the empty set is 0 and that mu is additive. In this case, this content is also monotonic and it is also sub-additive. To verify this, okay, so let's start with two sets in the ring, say A and B, and A is a subset of B. To show monotonicity, we would like to show that the content of the smaller set, A, is less or equal to the content of the larger set, B. For this, we need to write B in terms of A. So B is A union with B minus A. So we have here a set B and we have here a set A. So B minus A would be the annular region or this donut shaped region here. So if you combine that with A, you get the larger set B. Okay. And notice also that these are pairwise disjoint. So the intersection of A and B minus A is the empty set. Since we have a ring, it is closed under set difference. So B minus A is also in the ring. Hence, we could apply the additivity of mu. Say that the content of B is the sum of the contents of A and the contents of and the content of B minus A. So mu is additive. Okay. Since this a content is always non-negative, then the sum would be greater than the content of A. Hence, the content of the larger set B is greater or equal to the content of the smaller set A. And that is indeed monotonicity. Now, to prove additivity or sub-additivity, it is enough to prove it in the case of two sets because we have a ring. Okay, so in this case, take two elements of the ring. Then the ring is closed under union, therefore the union is in R. So taking or writing again the union as follows. So we can write the union of A and B as A union B minus A. And again, the set difference is in the ring. And take note that, again, A and B minus A is pairwise disjoint, since B minus A does not contain any element in A. Okay, with this, we can now apply, again, additivity of the content. So the content of the union is the content of A plus the content of B minus A. Now, we know that mu, the content, mu is monotonic, therefore this is greater than the content of A plus the content of B. Or I should say less or equal to the content of B, since B minus A is a subset of B, and we know now that mu is monotonic. Okay, so the content of B minus A is less or equal to the content of B, and this is subadditivity. And therefore, we have shown that a content is also monotonic and subadditive. So that's the first property. The second property that we would like to establish is the following. So if I have two elements in the ring, A and B, and A is a subset of B, and the content of A is finite, then the content of the set difference, B minus A, can be obtained by taking the difference of the contents of B and A. Okay, this assumption here is imposed in order to avoid the operation infinity minus infinity. So the content of B can be infinite, okay? And if it happens that the content of A is also infinite, then this vague difference is not well defined, okay? It is possible that the content of B minus A can be 0, can be a finite number, or can be infinity. So to avoid this operation, infinity minus infinity, we assume that the content of the smaller set is finite. So this coincides with our intuition. If you think of a content as the cardinality or the number of sets, if you count the cardinality or number of elements in the set difference B minus A, and A is contained in B, then you can count the number of elements of B and then subtract the number of elements of A. Okay, so for the proof of this, you could see that this follows immediately from the first, from the proof of 1. In particular, the proof of monotonicity. Okay. So to look at that, we take note that here we have this equation. So by subtracting the content of A both sides, you get the second property. Okay. Now for the third property, suppose we have a pairwise disjoint sequence of elements in the ring. And for convenience in the future, we will abbreviate this as PWD. And the union of this sequence or countable collection is also in R. Okay, we need to postulate this or assume that the countable union is in R because there's no guarantee that this ring is closed under countable unions. Then the content of the union is greater than or equal to the sum of the contents. Okay, this is similar to sigma subadditivity, but the inequality is reversed. And for this reason, let us name this as reverse sigma subadditivity, because the inequality now here is reversed. So let us look at the proof of this inequality. Okay, so we start with uh, taking only a finite number of sets in the union. So in particular, let us take the union from some positive integer capital N and take the content of this union. Now, since mu is additive, the content is additive, therefore the content of a finite union is the sum of the contents. So we have here the summation, the content mu an, n from 1 to capital N. Okay, now the finite union is a subset of the countable union. Okay, so in this case, we can now apply the first property, in particular, the monotonicity of the content, that the content of the finite union is less than or equal to the content of the countable union. Because the countable union here would be larger or a superset of the finite union from 1 to n. And from this, it is enough to pass n to infinity to get the reverse sigma subadditivity. Okay. Take note that the terms here are in reverse order, in contrast to this statement. Okay, so that's the first three properties that we would like to establish. Okay, so a content is monotonic and subadditive. The content of the set difference is the difference of the contents, provided that one is a subset of the other and the smaller set has a finite content. And a content satisfies the reverse sigma subadditive property, meaning the content of a countable pairwise disjoint union is greater than or equal to the sum of the contents. So in particular, we have the following direct consequence of this theorem. So we have the following corollary. This is the counting principle for contents. So suppose we have a triple, so X a set, R a ring, and mu a content. So we have this triple as a content space on, and the content mu is defined on the ring R on the set X. Okay, then if we want to take the content of the union, then this would be the content of A plus the content of B, and then in this case, A and B might have a common set of elements. So this intersection has been, the content of it has been computed twice, one as a subset of A and one as a subset of B. So to adjust that, we need to subtract the content of the intersection once. Okay, so that's the idea of this counting principle for contents. And this is valid for any uh, elements in the ring, of course, provided that the content of the intersection is finite. Again, to avoid the operation infinity minus infinity. So the proof basically is to write the union in a clever way. So we can write the union as A, union B, and I want this to be pairwise disjoint. Okay, so we need to subtract A. Okay, but that's the same as subtracting those elements in A that are also in B. Okay, so to visualize that one, so A would be this one, and the remaining part would be this region here. So this would be B, and you could subtract the intersection. So take note that the intersection is the one provided in this figure. Okay. And note that here, that the intersection is a subset of B. Okay, now we can now, and of course, this set difference here is also in R, or the intersection is also in R. Hence, by applying the additivity of a content, so mu of A plus mu of B minus the intersection. Okay, so we would like to emphasize here that as well, that A intersection B minus the intersection of A and B is the empty set. So in other words, the two sets in this union is pairwise disjoint. Okay, now, so here we applied the additivity of a content. For the second term, so the intersection being a subset of B, we call from the second property that the content of the difference of the content. Of course, provided that the content of the intersection is finite, which is the assumption here. So we can apply the second property that we have mentioned or we have proved a while ago. And that's the proof of this corollary. So again, the content of the union can be obtained by taking the sum of the contents minus the content of the intersection. Because as we have said, it has been counted twice, one as a subset of A and the other as a subset of B. So a remark, I would like to emphasize that this is valid for the corollary. It's valid for a finite number of sets. Of course, these sets should be in the ring. And this is basically the let's say inclusion principle for contents. So this is an exercise in the course notes, and in fact, in the second exercise, you will show a generalization or a modification of this inclusion principle. Let us emphasize that. So principle So an extension, as I said, of this inclusion principle is an item in your second exercise, and that's the Bonferroni inequalities. Okay. So before we proceed in considering contents and premeasures, let us consider the following definition. So suppose I have a sigma algebra, sigma, on a non-empty set X, then a premeasure, say mu, from sigma to the set of non-negative extended real numbers will be called a measure. Okay, so what's the difference between a premeasure and a measure? So for a premeasure, the domain can be a semi-ring. But in the case of a measure, it is required that the domain must be a sigma algebra. Okay, so that's the difference between a premeasure and a measure. And in this case, the triple, the set X, the sigma algebra on X, and the measure on X defined on the sigma algebra will be called a measure space. So X here is our ambient space. Sigma is the collection of subsets that we can assign a measure, and mu is the corresponding numerical measure. Okay, so let us provide several examples. So the first one is every Dirac premeasure on a sigma algebra is a measure. Well, this follows from the fact that we have seen that the Dirac is indeed a premeasure, and if you change or if you have a domain for the premeasure which is a sigma algebra, then by definition it is automatically a measure. So that's a quick example. For the second one, so let us consider a set X, the sigma algebra, which is the power set of X, meaning the set of all subsets of X, and the counting measure mu c. And we will refer this as the counting measure space. And how is mu c defined? So this is a function from the power set of X to the non-negative, extended non-negative reals. So given a subset of X, the counting measure from the word itself is the number of elements of the set if A is finite. Otherwise, meaning if A is infinite, then we set the value to be infinity. Okay. So let us verify if this is indeed a, uh, a measure on X. Since the power set is already a sigma algebra, we only need to prove that indeed this mu c is pre-measured. So the empty set has no element, therefore we set or this is equal to 0. Okay. Next, we need to show that mu c is sigma additive. So for that, let us take a countable sequence of subsets of X, okay, which is pairwise disjoint. And let us set A to be the union. So here we would like to show, or we would like to establish that the counting measure of A, which is the countable union, is the sum of the counting measures of the sets A sub n. Okay, since we have a sigma algebra, this is also a subset of X. In other words, it's an element of the power set of X. Okay, so here we need to distinguish two cases. What if A is finite? And the second case would be what if A is infinite? So first, let us consider the case where A is finite. In this case, A sub n would be non-empty only for finitely many n. Okay, and let's call them n sub 1, n sub 2, sub and up to n sub capital N. Okay, and at the same time, an would be empty for any n not equal to these indices. In other words, the counting measure of an would be 0 if n does not belong to this set of indices. n1, n2, up to n sub capital N. So from this, you take the cardinality or the number of elements of A, that would be the same as cardinality if we take the union of sets having indices n sub k, k from 1 to capital N. Because if n is not does not belong to this set of indices, then take note that A is empty. Therefore, they do not contribute to the union. Now, according to the remark that we have mentioned a while ago, more precisely the exclusion-inclusion principle uh, for contents. Okay, since the A and K's are pairwise disjoint, then uh, the cardinality of the pairwise disjoint union is the cardinality or the sum of the cardinalities. So here we have the sum of the counting measure, this case. Hence, I can add infinitely many zeros here. In other words, those indices that are not in this finite collection. To obtain our desired equality. Okay, so that is the case when the union, the countable union, is finite. So the other case is that what if this is not finite? Or what if it is infinite? Okay, so you have a pairwise disjoint collection, AN here, wherein the union is infinite. So there are two cases here. So either A sub n is infinite for some n. So if at least one of the sets involved is infinite, therefore the countable union will be infinite as well. Or AN is non-empty for infinitely many n. This is when AN is finite for all n. Okay. So if the sets involved involved are finite for all n, okay, and they are pairwise disjoint, if you want to have a union that is infinite, then at least infinitely many times this A sub n's would be non-empty. Okay. Otherwise, if uh, if it is not empty for only finitely many n, the union would be also finite. Okay, which is a contradiction to this second case when the union is infinite. Okay, so that would be the two cases. Either a n is infinite for some n, and from this you already know that the counting measure of the this set an would be infinity. And for the second case, this means that so if it is non-empty, the counting measure would be greater than 1 for infinitely many n. So in either case, we would have, so the counting measure of A, from this case, this is infinity. Take note that in the first case, if one of the terms in this series is already infinite, then the series would diverge. So this infinite sum here would be also infinity. On the other hand, if the counting measure of a sub n for infinitely many n would be greater than or equal to 1. So in other words, you're taking the sum of numbers greater than or equal to 1 infinitely many times. Okay, so in that case, this series would diverge. Therefore, the series would be equal to infinity. Okay, so in the worst case scenario, this counting measure here, okay, are equal to 1, meaning the a sub n's are singletons. So you add distinct singletons infinitely many times. Therefore, you would get an infinite series. Or a series whose sum would be infinity, meaning it would be divergent. So in either case, either the union is infinite or it is finite. We have established that the counting measure of the union is the same as the sum of the counting measures. So indeed, mu c is a measure on the set X. Okay. The next example suppose I have a sequence of measures. So this triple would be a measure space. And some coefficients, let's say alpha n, which are non-negative, for any positive integer n. Okay. Then, one, I can show that the triple so if we take the linear combination or an infinite linear combination of these measures having the weights alpha sub m, this is also a measure space. So, well, one has to show that this series here is also a measure on X. And that can be shown or established by merely applying the fact that each mu sub n are measures or is a measure, and then the alpha sub n's are non-negative. This condition here is included in order for us to guarantee that this series here would be always non-negative. Okay. And for our final example, we consider the so-called restriction measure spaces. And there are two versions of this. So let's start with a measure space, X, sigma, and mu. And a set E in the sigma algebra. So let us recall the restriction sigma algebra on an element of a sigma. So sigma sub E, recall that this is the set of all subsets of E that are in sigma. Okay, in the previous lectures, we have mentioned that this is a sigma algebra on E. Not on X, but on E. Then we define the restriction sigma algebra. So now this restriction is defined on sigma sub E. Take note that from this equation, we could see immediately that the restriction sigma algebra on E is a subset of sigma. And in this way, we define the restriction measure to be the original measure mu A. This is for any A in sigma sub E. So we basically follow the same definition as mu, but we are just restricting the domain of the measure to the restriction sigma algebra on E. Take note that according to this inclusion here, this is an element of sigma. Therefore, we can take the measure of this set A with respect to the measure mu. And from this, it follows that the triple E, this is now your ambient space, and this is your sigma algebra on E, and then the restriction, this is now a measure space. Well, to prove that this is a measure, one has only, or you only need to apply the fact that mu is a measure. In other words, the fact that the measure of the empty set with respect to mu is 0 and mu is sigma additive, that would imply that the restriction would also satisfy those properties. So I encourage you to write that if it is not clear to you. So this is one way of obtaining the restriction measure space by restricting the ambient space to an element of the sigma algebra. Now, another way. So what if I retain the ambient space, retain the sigma algebra, but restrict the measure? So this is a measure space where mu sub E is a function, is the measure from the sigma algebra to the extended non-negative reals defined as follows. So for any A, in the sigma algebra, mu sub E of A is the measure of A intersection E. Since a sigma algebra is closed under intersections and E is in sigma by assumption, this is also in sigma, therefore the right-hand side is well defined. So let us look at the proof of this example here. So suppose I have, let's say, what if I want to take the value of the empty set? So you just apply the definition. So this is the measure with respect to mu of the empty set intersection with E. The argument is just the empty set. Since mu is a measure, then it is a 0. Okay. The next step is to show that mu sub E is sigma additive. So for that, let us consider a countable collection of subsets of X, which belongs to the sigma algebra. And this countable collection is also pairwise disjoint. Then, if I take the intersection with E, the closure of sigma algebra under intersection implies that this sequence here, AN intersection E, would be also a subcollection of sigma, or they belong to sigma. And in fact, these are also pairwise disjoint, which you can easily show algebraically. So if you take, let's say, the intersection so for M and N that are distinct, you apply the associativity and commutativity of the intersection. Okay. And this here is equal to the empty set because the sets are pairwise disjoint. Therefore, the intersection is empty. Well, you can visualize this as follows. If you have sets, let's say A1, A2, A3, and so on. Okay. And then you have a set E. This would be your set E. If you take the intersection with the sets A sub 1, A sub 2, A sub 3, and so on, because the original sets A are pairwise disjoint, then the intersections would be also pairwise disjoint. So in this case, this is A1 intersection E, A2 intersection E, and then A3 intersection E. So the intersections with E are also pairwise disjoint. Okay, we've used this so that we can apply the additivity or sigma additivity of the measure mu. Indeed, we have the following. So let us look at the value of the pairwise disjoint union with respect to mu sub E. We just apply the definition of mu E. So this is AN intersection E. Then you can apply the distributive property for sets. Okay. And here you now use the fact that mu being a measure, so it is sigma additive, and we know that the collection AN intersection E is pairwise disjoint. Okay. So the measure of the pairwise countable disjoint union is the sum of the measures. And again, you apply the definition of mu E and recognize that this is the sum of mu sub E of AN. And this proves that mu sub E is also a sigma additive. Hence, mu sub E is indeed a measure on X. Okay, so these are the two restriction measure spaces. So again, the first one would be obtained obtained by restricting the measure on the restriction sigma algebra on E. So here you now have a measure space on the subset E. The other one is that you have a measure space. So same set X, same sigma algebra, but you have a different measure. So here your measure is obtained by taking the measure of the set intersection with the set E. So that's it for measures. In the next lecture, we will again revisit contents and pre-measures.